Hello student, good morning to everyone. What did we learn yesterday? Yesterday we learned about CH-1,3 dimethyl cyclohexane, that is AA or EE form. So today we are going to discuss about the remaining part, that is a B part. So that is again as a third type, that is a 1,3 type. So here B part we are going to learn, that is a what is that, trans now, right? Trans isomer. What type of the bond do you can you tell me what type of the bond, what type of the form it is, whether both the substituent present at axial, equatorial or axial equatorial? Yes, here is a 1,3 which is a AE, or we can call it as a EA form, right? EA form. Right now here also we are going to consider the general example is, for example, trans 1,3 dimethyl cyclohexane, right? Trans 1,3 dimethyl cyclohexane. And here, as we know that trans means what? Both the substituents are on the opposite side of the general plane, and therefore it is known as a trans. Let us see the structure of those. Here, as we know that this is one of the structure, one methyl group which is present at axial position. This is 1, 2, 3, 4, 5 and 6. Look at 1, 2, 3. At 3 position there is a one methyl group which is present at equatorial position, AE form. Now if you look at the methyl group, if you put a hand here, what do you see? This methyl group is above the plane. And second one, if you put hand here, this another methyl group which is below the plane, and therefore it is a trans isomer. Now look at the model. Observe the model carefully. What do you see? This is a carbon number 1, 2 and 3. At 3 position, this methyl group which is present at equatorial position which is below the plane, and this methyl group is above the plane. By looking as a model, we can very easily find out the cis and trans. This is a trans conformation, right? So you look this model very carefully, and one is above the plane, one is below the plane, and that's why it is a trans. Why 1,3? Because both the substituent, one which is present at axial position, one which is present at a equatorial position. Now what is the next point, or the this is structure, we can call it as this is a structure number 5. And after that we know that there is a flipping process, right? And after the flipping, what is happening there? In a flipping process, we are getting this carbon number 1 goes below the plane, and this way, this is a carbon number 1, 2, 3, 4, 5 and 6. Now look at carbon number 1 which is axial position, that goes when flipping is a process where the one of the chair conformation is converted into as another chair conformation, and during that process axial bond becomes as equatorial and equatorial bond becomes as axial. Now it becomes as equatorial. Look at 3 position, and this equatorial position below the plane, that is going to becomes as an axial one, and but the position of that methyl group remains same. Means one goes below the plane, one is above the plane, and therefore it is and this structure you can call it as a structure number 6. Now I am putting here ... What do you tell me? What is this? This is a mirror, right? And what is the purpose of mirror? You can see the mirror or images of the object. Now this compound looks here in this way, right? Here is a methyl group at this 1, 2, 3, 4, 5 and 6. Look at 3 position. What is 3 position? The methyl group is looks like this CH3, and as we know that there is a flipping process. This structure number is known as a 7-1. After the flipping, what do you get? After the flipping, you are going to get the structure like this. This is a what is that? Carbon number 1, 2, 3, 4, 5 and 6. One equatorial axial, that becomes as a equatorial, and equatorial becomes as a axial one here. And if you observe this structure carefully, what do you see here? This and these are the identical, and this is a structure number 8, right? So this is a so simple. Structure number 5, 6, 7 and 8 we got. And what are the point to discuss here? For second point, geometrical isomerism, we know that. Second point is optical isomerism. Optical isomers. What do you see? Optical isomerism. What is your opinion? Does this molecule or this molecule, whether this molecule is optically active or optically inactive? Here look at, for finding or for determining the optical activity, what do you see? You have to find out the plane of symmetry, because at T.Y.B.Sc level just as a plane of symmetry. If you cut this side, one is above the plane, one is below this side, there is a no plane of symmetry. Here what do you see? No plane of symmetry. No plane of symmetry, and therefore this molecule is expected to be optically active. This is a optically active molecule, right? Optically active molecule. And whatever expectation we expect here, that is come into true, means that is a true. Therefore this compound is optically active. Why it is optically active? Because there is no plane of symmetry. Look at the model here carefully. What do you see here? If you cut from here or either here, you won't get any symmetry there. There is no plane of symmetry is present, and therefore this molecule is optically inactive in nature. Now what is the next point to discuss about the third one? What is that? Conformational isomers. Conformational isomers or isomerism. Conformational isomerism, look at here, 5 and 7, what they are, and 6 and 8, what they are? The relationship between, they are the enantiomers. Enantiomer means what? There is a non-superimposable mirror images of each other, and therefore that type of the conformation is known as a enantiomers. Now if you look at this and this, they are identical. There is no diastereomers is present over there. All are the enantiomers. So these are the different structure. Now the last point we are talking about here, that is the fourth point, which is a relative stability, right? Relative stability. Now how do you calculate the relative stability? As we know that two things you have to remember. Find out the 1,3 diaxial interaction, and second one is a N-butane Gauch interaction. That is, and if one butane Gauch interaction shows 0.9 kilocalorie per mole. Similarly, if one CH3H 1,3 diaxial interaction is present, that is also shows as a 0.9 kilocalorie per mole. That are the energy, and we know that the general statement, if the internal energy goes on increasing, the stability of that conformation or that structure goes on decreasing. This is applicable to all the organic molecule, and therefore look at here. The one methyl group which is present at axial position, and therefore if the substituents are present at equatorial position, there is no question of finding the 1,3 diaxial interaction. There is no 1,3 diaxial interaction. Possibility only the butane-Gauch interaction, and that we have learned in case of the 1,2. In a 1,2 there is a butane-Gauch interaction, but 1,3 there will be a no butane-Gauch interaction. Right. Now look at 1, 2, 3. Here is a one of the hydrogen atom. Here 1, 2, 3. One of the hydrogen atom here. How many 1,3 diaxial interactions are there? 2. So 2 into 0.9 is equal to 1.8 kilocalorie per mole. This much amount of the energy associated with this conformation, and all are the same, and therefore it has 1.8. It is also has 1.8. This is also has a 1.8. This is also has a 1.8 kilocalorie per mole. I think these are the, in this way we have calculated, and the comparison between this conformations, 4 conformation we have seen about the 1,3 diaxial interaction. So comparison, energy comparison we will see in the next lecture. Let us stop today here. Have a nice day. Thank you.